Now, we mentioned in the last video that we may have to go through a different form of normalisation whenever we do subtraction. So let's look at an example here of subtraction, and we'll start off using the decimal values in order to give us some intuition. Now we're going to look at it in terms of what happens to the value of the mantissa whenever we do the subtraction. So there's going to be three options for the decimal. Either the mantissa is going to be a number which is less than 1, and this is called cancellation, and we'll see this just in a minute. Or the value for the mantissa is greater than or equal to 1 and less than 10, and this is the normalised answer, and we don't need to do anything to this because it's fully normalised. Now the other option is the mantissa is greater than 10. Now for subtraction that is never going to happen, which again we'll see just in a minute. So we'll look at each of these three here and we'll see what happens to the normalisation. So let's say we've got two numbers that are very close together. For example, 999 minus 998. We can write this out as 9.99 times 10 to the 2. We can write this one out as 9.98 times 10 to the 2. Now we can do the subtraction because the indices are the same here. So we're going to have 9.99 minus 9.98. So that gives us 0.01 times 10 to the 2. Now the answer here is less than 1. So the mantissa for the result, which is this number here, you'll see is less than 1. Now it's less than 1 because these numbers are very close together. And the closer they are together, then the smaller this number becomes. But we don't want the number to be in this format here. We want it to be normalised. That is, in the decimal system, we're going to have the result being greater than or equal to 1 and less than 10. So how are we going to get this number here so that it's greater than or equal to 1 less than 10? Well, we can see here that if we were to multiply this by the value of 100, then this will give us a value of 1. But if we multiply this by 100, in order to get the same answer for the result, we're going to have to divide this by 100. So the final answer is going to be 1 times 10 to the 0, which is a value of 1. So this is the normalised answer here. So this whole process here, whenever the numbers are the same, is called, as I mentioned, cancellation. So again, we'll look at this whenever we look at the binary representation. Now, the other option that we're going to have here is when the answer is an actual normalised value. So for example, 8 times 10 to the 2 minus 4 times 10 to the 2, then the indices are the same, so we can do the subtraction and we're just left with 4 times 10 to the 2. The mantissa is within the range 1 to 10, so it's normalised. So there's no normalisation required here. So there is a normalisation required here when MR is less than 1, no normalisation required here. Now what about the option where the result is greater than 10 whenever we do subtraction? Well, we can see that that is never going to happen. And it's never going to happen because the numbers which we will receive into our floating point unit will already have been normalised. So they'll always be in the range of greater than or equal to 1 or less than 10. So if we take two numbers within this range here, 1 to 10, and we subtract them off, then we're still always going to be left with a number which is within this range. We're never going to get a number that's going to be greater than 10. So this can never occur. So let's look at what happens in terms of the decimal, the binary system. Now let's look at the three binary equivalents. We're going to have MR is less than 1 and we'll have the cancellation. We'll have an option where MR is greater than or equal to 1 and less than 2, and an option where MR is greater than 2. So we'll look at the last two options here first of all, and then we'll look at the third option up here. So Let's say, for example, we have 30.4 minus 10.4 gives us the answer 20. 30.4 can be written in this format here, and 10.4 can be written in this format here. Now, if we want to subtract them, we're going to have to find the same exponents. So we're going to have to increase this exponent to a value of 4. So that's increased to a value of 4. So that's equivalent to multiplying by 2. So if we multiply this by 2, in order to keep the number the same, we're going to have to divide the mantissa by 2. So that's going to give us 0.65. So we've got the same exponents. That means we can now subtract. So we'll have 1.9 minus 0.65 is equal to 1.25 times 10 to the 4. So we can see here that this mantissa is within the range 1 to 2. So it means that we don't need to do any normalisation in this case. Now the option MR greater than 2 doesn't exist for the same reason it doesn't exist in the decimal case. That is, the values for our two numbers are already come in as a normalised number. So it means that those numbers for x and y are going to be in the range of 1 to 2. So it means whenever we subtract one from another, we're never going to get a number that's going to be greater than 2. So this just doesn't occur. Now the interesting one here is whenever a cancellation occurs. That is whenever the subtraction of the mantissas gives us a number that's less than 1. So let's look at an example here. We have 12.8 minus 12, which gives us a number 0.8. So that's equivalent to 1.6 times 2 to the 3. And this is equivalent to 1.5 times 2 to the 3. So we can subtract these off because they've got the same value for the exponent. So 1.6 minus 1.5 is 0.1. So you can see here that we've got a value of 0.1 for the mantissa of the result. That is, it's less than 1. So we have what we call here cancellation. So it means we're going to have to normalise this result because we want a number here that's greater than equal to 1 or less than 2. So how do we take this number here and generate a number which is greater than equal to 1 and less than 2? Well, in order to increase this mantissa, we can only increase it by doubling it each time because we're using binary. So if I was to try to double this number until we get a number that's greater than equal to 1 and less than 2, then I could double this once and I'll get 0.2, and then double it again, I'll get 0.4, double it again, I'll get 0.8, and double it again, and I'll get 1.6. So we've got a number 1.6 here, but we've had to double this 4 times. So if we've had to double this 4 times, it means that we're going to have to decrease this here by that factor as well. So we're going to be left with 2 to the power of 3, and it will be the minus the 4. So it will be 2 to the power of minus 1. But how are we going to find this factor of 4, which we increase the mantissa by, but decrease the exponent by? Well, we're going to find this by the leading zero count, and this is best seen on the Excel spreadsheet. So we will go ahead just in a moment and we'll put these numbers into the Excel spreadsheet, and you'll see where this leading zero comes from. So the increase in this mantissa is going to be by a factor of 4, and this factor of 4 will be the leading zero count. And the decrease in the exponent will be again by a factor of this leading zero count. So if we call the leading zero count lambda, then we can write it down mathematically as the normalisation for this cancellation that we get when we subtract is going to be the mantissa for the result, and it's going to be multiplied by a factor of 2 to the leading zero count, which is lambda, and the exponent is going to be decreased by that same factor of lambda. So this is important, and this is something that we have to note, and it's part of our new algorithm. So let's go ahead and we'll have a look at it in the Excel VBA tool, and it'll all become quite clear. So again, if you go into the resources section, you'll find the Excel file. And if you open that up and get into the Tools tab and click on our Add Subtract. Now we're going to put in the two numbers, our 12.8 minus 12. So we've got 12.8 and we're subtracting off the number 12 and we get the answer 0.8. So we don't need this here for now, so you can just press close and we've got the subtractions done here. Now we won't talk through all of this here. What we're really interested in is what's happening here at the Add Mantissa line. So at this point here, we're going to have to do a normalization, and this is the normalization here. So you can see here, if we were to count the number of leading zeros in the mantissa, you can see we're going to have 1, 2, 3, 4 leading zeros. So if we count the leading zeros, then what we can do is we can increase the mantissa by that 4 leading zeros. So in effect, we're taking this 1 and shifting up 1, 2, 3, 4 positions, which will normalise this. But if we shift this up by 4 positions, we're going to have to shift the exponent down by 4 positions. That is, we're going to take this exponent value and we're going to have to take 4 away from it. And that's what's happened in this line here. We've taken this exponent value and we've taken 4 away from it. And in this line here, we've taken the mantissa value and we've shifted it up by a factor of 4. And then we've got our final result here, which we've got by getting rid of the hidden bit. So that's the hidden bit disappearing here, and we're just going to be left with our 1, 0, 0, 1, 1, 0, 0. That's 1, 0, 0, 1, 1, 0, 0 for our result. So what I suggest you do is you put in a few other values there that are very close together, and you'll be able to see that the count for the leading zeros will tell us how much we have to increase the mantissa by and how much we have to decrease the exponent. Now over on the left hand side, you'll also see that I've got the leading zero count here, and I've got this value 4, so this is automatically counted, these 4 leading zeros, 1, 2, 3 and 4. And you can see that the exponent value here is the exponent of the largest exponent, which is EX, and we've subtracted 1 from the other, so we've got EX minus the leading zero count, which is a number 126, and then if we put that into our binary, then we've got our binary answer here, and that's the binary answer which we have here, 0, all the 1s and a 0. So go ahead and open this up and have a little play with it, and you could work through one full subtraction if you like, all the way from the top all the way down, and you could put in 2 or 3 different values and test it out and make sure you're getting the right answer and you understand how this is working, because if you understand how this works, then you'll understand the algorithm for both addition and subtraction of 32-bit floating point numbers. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.